Okay, the last unit, thank God. Biochemistry. It's the study of chemical processes relating to living organisms. Okay, basically, it's the study of the chemistry of life. As our little, and by the way, for those of you watching this at home, I started this. I didn't put it on here, but you should also type into a YouTube search Biochemistry Crash Course and watch the video on that we just saw. All right, it'll be the first one that comes up. And basically, it's Hank Green talking about what I'm going to talk about here a little bit, and only a little bit funnier than me, and certainly better looking. So that we watch that little video for an introduction, and but these are the actual notes. Oh, what am I doing? Idiot! I forgot. I got notes to give you. You don't even have to write your own notes.
Oh my
God. No. Hey, we're recording, so watch your language. All right, now this one.
I tell you, I don't need this paper anymore.
Yeah, you don't need paper. What I need to do though is somehow or other the copy machine people did not do what I asked them to do, or I asked the wrong thing, and they're stapled. Take the staples out. You do not need the staples.
Oh, you have one of those
You know
staple
what?
things?
I'm gonna leave it in. I'm gonna be a rebel.
No. You can't really leave it in because you won't be able to turn the pages once it's in the binder. All right, so you want to take out that staple and then put them into the binder in the same order. You're going to be using these and filling these in as we go along. Okay? You can get the staple out. You'll figure it out without puncturing and drawing blood. Of course, if you do draw blood, you can always write your notes in blood. That would be very useful in case if you don't have a pencil with you.
Okay.
All right. Back to the paper, back to the notes. Okay,
No,
so most of these notes, you'll notice the reason I did this for these notes, there are a lot of pictures when it comes to this biochemistry stuff. All right, I mean, there's a lot of different pictures of stuff that I got from either the internet or from your textbook or whatever, and they would help to explain it. If I had to draw all these, even the ones just on today's, it would take way too long. All right, so it's just nicer to have them here. So we're studying living organisms, the chemistry behind that, okay? All biomolecules, basically, are going to be carbon compounds. And I say that because with the eye towards next year or the year after, if you guys do take Chem 2 AP Chem, which would be a good idea for a lot of you if you're thinking about certain areas. We spend about a quarter of the year, maybe a little bit more, on organic chemistry, on carbon compounds. That's all that organic chemistry means. You know, a lot of times you guys hear the word organic, you think it means naturally grown. Well, you know, and that's true. They use it for foods. You know, it's supposed to be not using pesticides and chemicals and blah, blah, blah. But really, organic simply means it's got carbon in it. Anything that has carbon in it is organic, okay? And we're going to talk about that a lot in Chem 2. So I mentioned that here because I used to have this. I told you I moved it down to this chapter because I had to switch the redox stuff up to there. It's not really on the AP exam. And since that's an AP class, I thought I'd just finish it up with this. Plus, it's a nice way to finish out the year because you guys already know most of this stuff. Had it at least once in bio class. All right. What are the 4 types of biomolecules? You just saw Hank Green talk about this. All right. He mentioned the 4 types, the exact same 4 I'm going to talk about. Carbohydrates, lipids, nucleic acids, and proteins. And I will talk about all of those. Yeah, I just gave 2 there. Oh, here you go. All right. So let's start off with today, carbohydrates. Okay. Carbohydrates contain 1 or more sugar molecules. Okay. Sugar, saccharides. That's what the word saccharide is really referring to. It's a sugar molecule. And a whole more than 1 or more of them put together is going to be a carbohydrate. Now we can have, well, their use I should talk about first. Their purpose is to give you energy. And they're really easy to digest and get instant energy from a simple sugar molecule, 1 or 2 sugar molecules together, glucose, fructose, galactose, all these different ones that you probably remember learning in biology class. All right? Well, they're the first thing that you digest. They're the first thing that you get energy out of. Okay? There are 2 types. The sugars, which are basically monosaccharides or disaccharides. And he mentioned a couple, and I will mention the same ones pretty much. That guy, and you should put a name. I don't think the name is underneath these, even though I have the structure drawn on there. Is called glucose. Okay? That would be a monosaccharide. A disaccharide would obviously be two of those guys together. It doesn't have to be two glucoses. It could be a glucose and a fructose, in which case that would be sucrose. Okay? And you could have, I think maltose is another one, which is two glucose molecules together. They all have a slightly different taste. They all have a slightly different structure for these sugars. Okay? And of course, the only thing we're really looking at right here is whether they're mono or disaccharides. You should be able to tell that by looking at how many of them are together. All right, and that's pretty easy. Okay. Now, you got that?
Yeah.
Okay. Polysaccharides, as you'd expect with the word poly in it, it's got many saccharides together, right? Big long chains of sugar molecules, which we use to we don't, plants do, I mean we do too, use to store our sugar. Because I can't, I'm not eating all the time, okay? Although some of you guys here eat all the time. But I'm not eating constantly. So when I'm not eating, I got to have a way to get energy. I got to have some storage form of this sugar. And I store them in a couple of, plants store them in a couple of different ways. They store them as starch, which you're all familiar with, right? You all know what starch is. Potatoes are starchy. Pasta is starchy, right? Popcorn, starchy. All right, all of those. It's the edible form of storage sugar in plants. Potatoes, pasta, popcorn, all the P words. Anything that begins with a P has starch in it. Just kidding.
Pigs.
Pigs. They probably have some starch in it. I don't know. No, not pigs. Plants. This is the plant's way of storing starch, of storing sugar, I should say. Okay, and his structure is very similar. And he just briefly mentioned that. I'm going to show you a little bit closer and talk a lot about it in organic in Chem 2 in a minute. But let's also talk about the other way it stores starch, and that's cellulose. Cellulose is the indigestible storage form of sugar. We can't digest it. Certain things can. Termites can. They can eat wood. Cows can. There are certain things, certain animals that can digest cellulose, but we can't. And I'm going to stick with the P words. Obviously, wood and stem doesn't begin with a P. So what I'm saying is the difference between eating a potato and eating a piece of paper is really in this picture. All P words. Potato, picture, paper. That's it. Look at this. That's starch. You have the same drawing on yours. And that's cellulose. They're exactly the same molecules. But what's different between that guy and that guy? Yeah, they're flipped upside down. Every other one in cellulose is flipped upside down. In starch, they're all arranged the same way. You say, well, how could that possibly make that much of a difference? It's the exact same molecule. All right, well, that's the crazy part when we get to organic. We're going to learn about something called isomers, and lots of different isomers. And we're going to learn about things like stereoisomers, which are identical about everything about the guy, except for the one atom is rearranged around. Like the same exact guys are there, but just rearranged around a little bit differently. But the structural formula will be the same. And the difference between that can be a poison and a drug that helps you. Like the classic example of that is thalidomide. Thalidomide in the 1950s or 60s, I guess. 50s, I think it was a drug given for morning sickness. And it did help with morning sickness for pregnant women, but it also caused birth defects, like babies born without any arms and legs. And in America, we didn't have a whole lot of those problems. And the reason why is the FDA never approved it. But in Europe, they did. A lot of birth defects because of that. The only difference between the thalidomide, they're both the exact same compound. One was the R configuration, the other one was the S, but other than that, it's pretty much the same. Yeah.
Isn't that in the song We Can Start?
Exactly. We didn't start. I play that when I do that in Chem 2, when we have a whole thing on that in Chem 2. We didn't start the fire. Children of thalidomide. Yeah, very good. Which is by Billy Joel. All right. Shout out to Billy Joel. He's rolling over in his grave right now. He's not dead. He's just got into the grave.
His empty grave.
His empty grave. Anyway, glycogen is the storage form for us. We don't make starch. So if you said about pigs, nope, it would be glycogen. Glycogen is our storage form.
P words.
Yeah, there go no more P words. Yeah, we had paper, picture, pasta, potatoes, plants, glycogen. So it's easy to tell apart. All right, so the glycogen is the way we animals, you filthy animal, store sugar. And like he said about glycogen, that's again a quick way to get it. All right, that's the next thing after you exhaust the sugar in your blood that's hanging out, and you've burned all of that up that you've eaten recently. Then you're going to go to your glycogen and start, drawing on that. What are you eventually going to draw on? I'm going to get to it tomorrow. Yeah, your fats. And you know what?
Protein.
This is exactly. If you wait long enough, exactly. If you don't eat long enough, you're on a desert island and you're starving, and you've exhausted even the sugars, the glycogens, and the fats, you're going to start burning muscle too. I mean, there are ways to get energy out of it. It's just that it's not really healthy.
So like in that situation, would a fat guy last longer than a skinny guy?
Oh, absolutely, sure, no doubt about it.
Also, if you get hungrier.
Yeah, if you're skinny, you're going to die faster on a desert island if all you've got is water. Now, I guess there could be confounding factors. For example, you may be in better shape than the fat guy whose body couldn't, may die for other reasons, might have a heart attack or something else. I don't know. But certainly energy-wise, he's got more to draw from than you do.
Does one burn faster than the other?
Well, you're going to do them in order. You're not going to start burning. And that's one of the reasons it's so hard to lose weight. So easy to put on weight, and it's so hard to lose it because the first order they're going to go. As far as how much energy you can get from them and how it's easier or harder, I'm sure you can do the calculations for the thermodynamics of it. But the point is your body's not stupid. You don't want to start with the protein. You want to start with stuff that's outright in your bloodstream already. And like I said, a lot of the glycogen is stored in your muscles, so it's readily available anyway. There's just a picture of some cellulose, what it would look like, but not a big deal. Now, we will stop here because tomorrow we're going to pick up with lipids. I don't want to start lipids today. All right?